I'm in the zoo with the lions and apes and bears. You probably won't make it there. One of the options, they say they want smoke with me. You don't want to take it there.
What's up, guys? So we're here at the NYU Center of Quantum Information Physics, and today's topic is going to be how do people make a quantum computer? So yeah, Lucas, take it away.
Yeah, sure. Thanks. So there are three main parts in making a quantum computer. So the first part of making a quantum computer is the materials growth. So this is where we actually make our materials stacks that we then use to make computer chips later. Then two is the nanofabrication. So this is where we actually make the circuits, patterns, and devices that go into a quantum computer. These are the actual computer chips. And then the third part is the measurement and characterization. And so this is what we use to interrogate what devices we made, how they work, and how we can possibly make them better.
All right, guys, actually, we're going to be starting off with a high-level overview of quantum computing and also just what a qubit is. So yeah, let's go over that.
Yeah, sure. So the first thing with quantum computing is actually knowing what is a qubit, right? How do we make these things? And so the way we make these things is that we need what's called a two-level quantum system. So what does that mean, right? A two-level quantum system is any system in quantum mechanics where you can take two energy levels and individually address them without worrying about the rest of the system. So what I mean is, let's take an atom, for example, right? So an atom has a nucleus, right, that we're not going to worry about. So it's just going to be here. And then we have electrons, right? Let's take hydrogen, only got one electron, easy, right? Okay. So all of you probably remember, to some degree, at least from an introductory science course, that atoms have electrons, and the electrons orbit around the nucleus of this atom, right? Those of you who have taken quantum mechanics or chemistry, you probably know that these orbits are a lie and they're orbitals, but this is a good enough picture for now. So we're going to stick with this, right? So what we can imagine is, let's take one of these orbits and call it our zero state, right? And now let's take a higher energy orbit out here and call this our one state. Now, what we can do is we can use a laser that has the same energy as this transition, i.e. the difference in energy between 0 and 1, and we can shine that laser on this atom to promote the electron from the 0 state to the 1 state. That would be basically a NOT gate, right? Mm-hmm. So what you're doing is you're taking your atom from the 0 state to the 1 state, and you're not worrying about any of these higher energy levels outside, right? Because there are a bunch of different orbitals that you can have, basically places where the electron can go, but they're all individually addressable because they all have different energies, right? But if we call this the 0 and this the 1, and forget about everything else, we can drive transitions just between these two states, and that'll be our qubit, okay? So we do a very similar thing in superconducting circuits, right? We have a 0 state and a 1 state, and they have different energies. And by applying microwave pulses between them, we can convert between the 0 and the 1 state and apply logic gates.
I see. Cool. So this picture seems to be very analogous to a transistor, where we have a 0 state and a 1 state, and we just move back and forth. So where does the superposition come into?
Right.
Yeah. Like,
exactly.
How does it exist somewhere in between 0 and 1, or is there another axis that affects it?
That's a great question. Okay, so you're not existing in between 0 and 1 in the sense of, like, your electron's not going to be here. You'll never find your electron here, right? When you measure your electron, remember, these states correspond to an energy, right? And so you will measure your electron to either have this energy or this energy. You'll never measure a value in between. So that's what it would mean for the electron to lie somewhere in the middle here. So that's not exactly what's happening. So in reality, what's happening is superposition is just a fancy way of saying probability.
Right.
Okay. So what can actually happen is we can draw what's called the wave function of our electron, which is basically a function that describes the probability of us measuring our electron in one state versus another state, right? And we draw these wave functions, we write them with little angle brackets. It's just the convention in the field, okay? It tells you that you're talking about something quantum, right? And so we call the wave function psi, this Greek letter, and this is going to describe the probability of us being in one state versus another state, okay?
Mhm.
And so to put our qubit into a superposition, what we'd write is A times 0 plus B times 1.
Mhm.
And so what this is telling us is that our qubit has probability A squared. Really, it's the mod squared because A is a complex number, but again, don't worry about that.
Mhm. Yeah.
Right? So the probability is A squared that we measure it in the 0 state and B squared of measuring it in the 1 state.
Mhm.
And so our our system doesn't exist in the middle here, right? We don't have an electron that's just sitting in between these two orbits. But if you think about it as this is A equals 1, right? And this is B equals 1, then you're kind of in between,
Mhm.
right? Because A and B are going to change depending on your superposition.
Mhm.
So, for example, if you were to apply a Hadamard gate, right, which
Okay.
is the the gate that puts you into an equal superposition of 0 and 1, you would be equally likely to get A and B, or A and B would have to be the same value, right? Since this is a probability, the probabilities A squared and B squared have to equal 1. And so if you do a little bit of algebra, you would get that the Hadamard gate acting on the state 0, right,
Mhm.
is going to equal 1 over the square root of 2 times 0
Mhm.
plus 1 over the square root of 2 times the 1 state.
Mhm.
Okay? And so what this says is that we have an equal probability of measuring the 0 state and the 1 state.
Mhm.
Okay? And so when we talk about superposition, we're not talking about an intermediate energy. We're talking about the probability of measuring one state versus another state.
Mm. So I guess now, like the naive approach of attaining a Hadamard gate is to shine a beam of photons with an
Mhm.
amplitude of somewhere that's not this difference, maybe like half of it.
Right.
Is that like correct? Because that'd be kind of weird if the electron can't live in
Yeah.
between these states.
So you're thinking along the right lines, right? We definitely want to control what kind of pulse we're applying in order to apply a gate, right?
Mhm.
But you don't want to actually apply a different number of photons, right? Which is what the amplitude would be.
Mhm.
What you want to do is apply a slightly detuned frequency. Detuned frequency means if this is your energy for the transition, right? You want to apply a pulse of light with a slightly different energy.
Mhm.
Energy of light is related to its frequency, so we call the frequency detuned.
Okay.
So if we apply, let's say, this kind of frequency, and we apply it for a certain amount of time, which completely depends on the physical system and parameters of your specific quantum computer, we can put our system into a equal superposition, and that would be a Hadamard gate. So the actual implementation, the physical implementation of the gate, is a laser shining at a slightly detuned frequency for a certain amount of time.
I see. Cool. And is this like difference in frequency like the same exact concept with like the color of light? And because like there's each color has a different frequency, which would mean different energy. And is this the
Mhm.
same exact concept?
Yeah, exactly. So again, it depends on the physical system, what actual color laser you're using to drive the transition from 0 to 1. But if your transition from 0 to 1 was let's say it was blue, just for some reason,
Yeah.
right? Or let's call it green, because that's right in the middle of the visible spectrum,
Cool.
right? If you were say your transition from 0 to 1 was green, right?
Mhm.
Then slightly detuning it, meaning slightly lower energy, slightly lower frequency, you would be changing the color slightly from green,
Mhm.
right? And so if you have lower frequency that's higher wavelength, that's closer to red. So it would be on the redder end of the visible spectrum, slightly detuned away from the green.
Yeah, that makes sense to me. Hopefully it makes
Sweet.
sense to you guys. And I guess we'll just continue on the tour now.
So, the first thing, like I said, is molecular beam epitaxy. This is what we use to actually grow our samples. Now, when I say grow, a lot of people are confused. What do you mean grow materials, Lucas? Well, when you actually make a material stack, right? So you make these wafers that have, silicon or germanium or whatever you use in a computer chip, the way these material stacks are made is that you take a wafer, which is a substrate, and you sequentially plate material on top of it, right? And so the way that you do that is by molecular beam epitaxy. So what we do is we take our sample, and let me get you a wafer so that you can see. So here's a wafer, right? It's a thin, very, very thin piece of material. And so what we do with these wafers is we load them into this load lock chamber. This load lock is an isolated vacuum chamber that's separate from the main chamber, which is all the way in the back. That's the big chamber, right? And so what we do is we load these samples into the load lock, let them depressurize, then load them into the main chamber. And when we do that, we can take our sample and we can plate it with material from a source. That source material is a solid phase crystal of whatever material that we want to grow. So say we have some indium we want to grow, right? What we do is we take a crystal of indium and we heat it up really, really hot. And when we heat that sample up really, really hot, what happens is it sublimes. So it goes from solid to gas phase. Sometimes molecular beam epitaxy sources will go solid liquid gas like normal, but often they'll also go solid gas. And the reason is because the pressure is so low. Either way, whatever happens, your source starts going into the gas phase and diffuses across your chamber over to your sample, right? And so what you get is that the source plates onto the sample in atomically thin layers, okay? So one of the techniques that we use for molecular beam epitaxy that makes it special is called READ, which is reflection high energy electron diffraction. READ is really important because it allows us to, in real time, monitor the growth that's going on. And so what we actually do is we take our wafer, right, if my hand's the wafer, we shoot a beam of electrons at a very grazing incident angle, so like a couple degrees, right? And we shoot this beam of electrons and hit our sample and it diffracts off. And the diffraction pattern that's created by the electrons is displayed on a screen. We take pictures of that, and then we can see from the diffraction pattern things about our surface. So we can see if the surface is rough. We can see what geometry the surface is crystallizing in. We can see a bunch of different things. And these are really important to understanding the actual interfaces and layers of our material. And so what we have here is basically a two-chamber system. So this is the load lock, right? So if you look in here, you can see a little puck. That's for actually holding the sample. So this thing right here, right? So this right here is for holding the sample. And so what we do, this is isolated by a gate valve right here. And so we close this gate valve, and that allows us to keep this chamber at vacuum while we vent this chamber so that we can actually load a sample in, right? So I can touch the outside of this, that's fine, but I can't touch the inside because a fingerprint will actually outgas and raise the pressure of our chamber. So yeah. So anyways, what the first thing I would do is I would take this puck out and I would load my wafer onto this puck, right? Then what I do is I close this window and I would turn this pump on. The pump's already on. And I would wait for this thing to get down to low pressure. Low pressure for one of these kind of gate valve areas, we call it a load lock. Low pressure is about 10 to the minus 5 torque, which is about 1 million times below atmospheric, no, 10 million below atmospheric pressure, which is really low pressure, but it's not billions, which is what this is. So what we do is we wait for this to go down to low pressure, and then we open this gate valve, and we use this transfer arm right here to bring our sample down into this chamber. And when we bring the sample down into this chamber, there's a thing right here. It's a locking mechanism that goes all the way into the chamber, and you basically dock this onto this. There's an arm that comes out and latches onto your sample, right? And so then what we do is we transfer this sample into here, and we bring this arm back up and close this gate valve, and now our sample is isolated in this chamber, and this gate valve is closed, so it's isolated from this, right? And so what we do then is we can start the growth, right? And when we start the growth, what happens is the material, like I said, is heated up, or the sources are heated up. These are some of the sources. They're heated up to a really, really high temperature. And when they heat up to this high temperature, they go from the solid phase to the gas phase and diffuse across your chamber. And when they diffuse across your chamber, they can hit on top of your sample and plate onto your sample. And so by controlling the temperature, we control the rate of that solid to gas transition. And that's what lets us determine how much we're growing. So this is our camera for the read for the read experiments, and it lets us actually take pictures of the electrons that diffract off. And so we can see how the electrons diffract off. They actually hit into this fluorescent sheet, and the sheet fluoresces when electrons hit it. And so if you were to take this off, and we had a sample in there right now, you'd actually see the pattern with your own eyes reflected on the screen. And so this just takes a picture of that screen, sends it to that computer, and we can measure the pattern to understand our circuits. So it lets us have this real-time control of what we're doing. Wow. So the next step in the device making process is fabrication, right? And fabrication is something that we don't actually do at NYU. We do fabrication somewhere else. We actually do it at City College. And the reason is just because we don't have the equipment here. And so what we do is use a technique mainly called electron beam lithography to define our circuits and wires that we actually use on our chips. And so the way this technique works is, say I have my chip right here, right? So the first thing that I'm going to do is I'm going to cover my chip with a polymer, right? And so the point of this polymer, it's some chemical that when you heat it up, it hardens into a mask, right? And so this is called a lithography mask. And the point of it is that we can then basically shoot a beam of electrons at it to crack it, okay? So say I wanted to, I don't know, write something like Nang. What I would do is I would shoot a beam of electrons at this pattern, right, in your name, right, in Nang. Mm-hmm. And what would happen is you would get this. So basically, everywhere that the polymer was that the electron beam didn't touch is completely just left as normal. But everywhere that the electron beam touched, you broke your polymer. And so what you get, and these lines would actually be much more continuous, so you just get the letters of the name defined. But then you can put this in a chemical developer, and what you get is just NaMg, and the polymer everywhere else, but you've washed away all of the cracked polymer. And so what I can do then is now I can use a chemical etchant to just etch the material that I exposed, right? The etchant will not etch this polymer, but it will etch the chip that's just kind of sitting there, right? Mm-hmm. And so what I can do is etch, right? And when I do an etch, now I still have this polymer, so it's going to look very similar, right? But there's going to be a hole in the shape of Nang, right? And so imagine that this is a hole that's set in the chip now, in the shape of the letters, right? Mm-hmm. And so once I do this, then what I can do is wash away the rest of the polymer and just leave the chip with Nang on it. And so I wash away all this polymer that was hardened, right? And I've still left the part that I've etched, right? So the etch is still there. It says your name, but the polymer is gone. And so we have the chip, but we have features defined in this chip at a very, very precise level. These features can be tens of nanometers. Wow. So they're really, really small, and you can define very, very thin features, which is what allows us to make these computer chips with billions and billions of transistors, like Intel does, right? So yeah. So this is electron beam lithography. It's one of the most powerful techniques that we use, and it's kind of what allows us to make the qubits that we make. This is one of our measurement labs. In this lab, we have 2 dilution refrigerators. They are here and here, and they're like these big metal cases are dilution refrigerators. And inside this dilution refrigerator is probably the thing that most of you would recognize when you Google a quantum computer. So when you Google a quantum computer, there's going to be probably a picture of something that looks like a chandelier. It's like this thing with a bunch of different stages. It's like a sciencey steampunk chandelier. It looks really weird. But what that is the cooling stages of a dilution refrigerator. And so at each plate, you get down to a certain temperature, and that temperature decreases as you go down and down and down in the fridge. And so the actual quantum computer is just a really small chip about this size, and it's at the bottom of the dilution fridge in a little cage. And so you don't actually see the chip most of the time when someone shows you a quantum computer. What they're actually showing you is all of the kind of surrounding hardware that encases that chip to make it cold enough to actually work. So just so you know, for example, if you warmed a qubit up, if you warmed it up to 600 to 700 millikelvin, so even below 1 Kelvin, you basically lose all your information. So you have to get these things really, really, really cold in order for them to actually work.
I see.
Yeah.
And that's because the heat will transfer some energy onto the qubit state?
Exactly, yes. And so the heat transfers energy into the qubit state. We call that thermal noise. And that thermal noise can scramble around your information, and you lose information.
I see.
Yeah. So this chip is a broken chip. But generally our chips are usually, about a square centimeter, maybe a little smaller.
Okay.
And on one of these chips, you might have 3 to 4 qubits in our case. But if you were at some silicon spin qubits group, that might be a different number. Or if you were at some NV diamond centrifuge qubits place, that would again be a different number. It completely depends on the type of quantum computing architecture that you're using, because the different qubit designs are kind of intrinsically related to that. And so a qubit made on a superconducting circuit looks completely different from a qubit made on silicon for spin qubits. Mm-hmm. So yeah, for this chip right now, our design would be about 4 qubits. We could probably cram a bunch more on there if we needed to, but we don't. We don't end up putting a ton of qubits on these chips because, again, our goal is not to make a 100 qubit quantum computer. IBM's already doing that. Our goal is to do some interesting fundamental new physics that unlocks new devices that might push the field forward in a different way. So our goal isn't just to optimize, make as many qubits as you can on a chip. Other people are doing that, and they've kind of optimized the process for doing that. Our goal is kind of, let's see how we can push the field in new directions and go to the absolute edge where no one's ever been before and push a bit.
Wow.
Yeah.
Inspirational. That's great. So how did this one break?
This one broke. It was really sad, actually. I worked for like a few hours sputtering aluminum on it. And what actually, it's a really dumb thing, but when you're sputtering, which is basically a technique similar to molecular beam epitaxy, when you're sputtering, you have to stick the chip onto a cup to hold the chip using copper tape. And so I was peeling off the copper tape, and the chip just broke because I peeled off the tape too hard.
Oh man.
Yeah, that's life. That happens sometimes.
Yeah.
But it all worked out, and I made this one instead. So.
That's it.
Yeah.
So how long does it take for you to, let's say, start to finish, make that chip?
So start to finish, through the whole process, the materials growth, the characterization, then the fabrication, and then the measurement. Going through all those steps can take about, I'd say, if you optimize it, 3 or 4 days.
Okay.
But realistically, probably about a week. But you can do multiple chips in parallel. So the reason for that is the molecular beam epitaxy growth takes a long time. It takes about a day to grow a sample. Really, it's like 8 hours, but like people aren't going to be growing for 24 hours. And often you'll grow multiple samples at a time. So you'll do an 8-hour growth and then another 8-hour growth without opening the chamber, and then you'll pull them both out. Right? Okay. So you do the growth, that's a day. And then you take that chip and you do some post-processing on it. Maybe you want to add some more of one element, like aluminum, or tantalum, or niobium. And so if you were to do that, you would sputter on top of that sample to get more of the material. And so that takes a couple hours. And then on that same day, you could go to the clean room, the nanofabrication facility, and you could go make a device, right? Mm-hmm. And so that's another day. So first day growth, second day kind of doing post-processing and fabrication. And then you actually take that chip and you put it in the fridge and you cool it down. And the fridge cool down process can take days. These fridges, again, they're getting to such cold temperatures that the actual process of bringing them from room temperature down to base temperature can take 1 to 2 days. And so once you do that cool down process, then and only then can you actually do the measurement, right? Because if you're not cold enough, then you're not going to get any signatures in the device. Mm-hmm. And so we get down to this base temperature, and then we can characterize our chip. And that whole process, again, takes, on average, about a week. This is a normal fridge set up for microwave measurements. And so you're doing a lot of stuff with alternating current here. Most of our fridges actually, or this fridge and this fridge both are set up for microwave measurements where you're doing alternating current things. And so this is basically just I don't want to say bare bones because it's still a dilution fridge, but it doesn't have any magnets in it, right? And I'm comparing it to this fridge, which does have magnets in it. This fridge has what's called a vector magnet, which is a magnet that controls or can vary the axis along which you apply a magnetic field. So you can apply a magnetic field in the X, Y, or Z direction. I don't remember the directions, like the strength to direction, but like one of the directions is 1.5 Tesla, then 3 Tesla, then 6 Tesla. For a reference on that, an MRI machine is usually 3 Tesla. So MRI machines are very strong magnets. Remember, you can't go into an MRI if you have like a hip replacement or something like that, where they put metal in you, because it'll literally suck the metal out of you. Oh. So these magnets are really, really strong. There's actually caution tape on the floor for some of our stronger magnets, because it's basically the line past which you cannot go with a pacemaker. So, yeah. So these magnets are really strong, and the purpose of them is that applying a magnetic field to our devices can change the material properties, or can help us realize some new physics that we have not seen before. And so studying quantum computers and studying the materials is kind of just one aspect when you're doing it at no magnetic field. When you introduce the magnetic field, remember, electromagnetism is not just electricity, it's electromagnetism. Right. There's a whole other side of the coin that you have to introduce in order to kind of reach a bunch of interesting physics. Mm-hmm. And so we do that using these magnets and fridges. So we bring our samples down to this really cold temperature, and then we apply magnetic fields while we're doing our measurements, and see how those fields affect the measurement. I see. Yeah.
I guess one question about tying it back to the whole quantum computer thing.
Yeah.
So in those fridges, you have the chip, which you would consider to be a quantum computer.
Yeah. So the actual chip itself is what's doing all of the computing, right? Mm-hmm. Everything else that surrounds that chip is just basically, cooling wires to and from the chip, other kind of sensors, stuff like that. You can think of it as like everything outside of the actual CPU chip in your personal computer at home. So if you've ever built a computer, for example, right, you have all the cooling fans, you have the housing, all of that stuff. That's kind of like what the dilution fridge does. But the actual computer is the chip.
I see. Yeah. So you have the chip. Mm-hmm. And I guess my question is, for the chip to do anything useful in quantum computing, there's this thing called a quantum circuit, correct?
Yes. Yep.
So how are you guys passing through qubits through these gates that I've been hearing about?
Yeah.
And is it something that's etched into the chip and it's like hardwired, kind of like an FPGA, or is it something that you do in a different way, like programming code?
Yeah. So that's a great question. That was one of the questions that I had going into quantum computing, is like, how do you actually physically realize these gates, right? Mm-hmm. Like, how do you make them? Because I was under the impression for a while, like as a layman who didn't really understand anything about quantum computing, that these were physical things that were happening, like that you were kind of making into your chip, right? In reality, these gates, what they are is they are signals that you send to a chip that already exists, right? And so again, I'm going to give you the neutral atom example, right? The cold atoms, because it's the easiest thing to think about, right? Let's say we have a grid of cold atoms, right? We just have them in a vacuum chamber, and that's our quantum computer, right? Let's make it even simpler. We have one cold atom, one qubit, right? All right, let's say I want to put that atom into a superposition of the 0 and the 1 state, right? So I want to apply a gate to it. That would be a Hadamard gate if I made it an equal superposition. That's what it's called, right? So if I want to apply a Hadamard gate, what I would do is I wouldn't do anything to that atom, like changing the atom or moving it around. I would shine a laser at it. And I would shine a laser at it for a certain amount of time, corresponding to the amount of time it takes to put it into that superposition. In the same way with superconducting circuits, the actual gate operations that you're doing are microwave pulses. So you're putting in electrical pulses for a certain amount of time into a circuit that already exists. So you don't actually physically pattern a gate onto a qubit, right? You can think if you were going to do that, it would be really hard to make these quantum computers robust, right? If you want to make a different algorithm, that means you have to make a different chip, right? But that doesn't really help us. So the best thing that you can do, and it ends up working out that that's the way it's done, is that you apply these different pulses to your chip, and those different pulses will put your chip into different quantum states, and that's your operations.
I see. I guess my next question is then, when we have a quantum circuit, like I was looking at some quantum circuits that are pretty complicated, it has a lot of steps. And I assume like these have to be chronological or sequential, right? So like, what is the time that it takes for you to send like a pulse and have to wait so that it's like in a steady state that you can continue on your circuit? And yeah, like what's the current status on that? Like, is it a whole field where they're trying to make it faster? And like how stable is it?
Yeah, so that's a really, really good question. Generally in the field, it completely depends on the device architecture. So some devices have clock speeds of megahertz. There are some companies that are kind of trying to push that to gigahertz. But clock speed is definitely an issue, right? And so that basically relates to how quickly can you apply gate operations sequentially one after another.
Right.
I don't actually know the answer to that. It's a good question. But yeah, it's definitely something people are thinking about. So, yeah.
Well, I mean, from what I've seen on my circuits, I run on like the IBM computer. Seems pretty fast enough.
Yeah, exactly. Yeah, it's pretty fast. It's definitely, hundreds to millions per second, or thousands to millions per second of gates that you can apply. But, if you think about classical computers, they're doing more than that, right? Clock speeds are really, really fast. Exactly, gigahertz. And so I want to say that we're in the megahertz regime right now, and we're trying to push to gigahertz, but that's not something that specifically we're trying to focus on right now.
I would even think that's not even the biggest concern for quantum computing, because they're trying to, I guess, improve the big O time complexity, right? And so one run of a long circuit is definitely it's going to scale if it's just one run. Way faster than any classical computer.
And actually that kind of brings up an interesting point, which is that quantum computers are one of the most interesting things about quantum computers is that you can take a quantum algorithm and you can run most of it on a classical computer and then pick the one part that's actually sped up by a quantum computer and run it like quantum. And so a lot of kind of what we see as the future for quantum computing is hybrid classical quantum computing, where you run most of the algorithm on a classical computer, but then you take that one part that's really bad time complexity scaling and you run it on the quantum computer, which can process it faster. And that way you don't have to worry so much about this overhead, but you can still get the speed up that comes from the quantum algorithm.
Right. That makes sense to me.
Yeah.
One thing I'm wondering then, in theory, you talk about quantum computing being useful for certain use cases.
Yes.
What are some examples of these certain use cases that would be better than a classical computer? Yeah.
So kind of the main applications for quantum computers are kind of seen a lot in first computational chemistry, so pharmaceuticals. Then also kind of the financial sector seems to be interested in quantum computing. I don't know too much about that stuff in terms of like the applications. I think that is kind of a little bit further off because they need a lot more qubits to do the stuff that they want to do. Then there's also, so there's chemistry, there's financial applications, there's encryption. So quantum computers, you probably heard, can break RSA encryption.
Right.
So that's a big kind of issue. There are actually, I've heard this kind of through the pipeline of like social media and news and stuff, but there are apparently companies and organizations that are stockpiling information, like encrypted information that they cannot break right now, waiting for quantum computers so that they can go back and decrypt all of it because it's an RSA.
Oh yeah.
And so that's a possible huge issue, right? Is that, you know, once these quantum computers are unleashed on the world, we might have tons of encrypted data, you know, credit cards and the like, just out there. Right. And so that's a huge potential issue. But yeah, those kinds of three examples are kind of three of the most prevalent that you know, I and many others see quantum computing being useful for. The one closest to me is chemistry. And the reason is, well, first, I got my undergrad partially in chemistry. I did a double major in chemistry and physics. And so computational chemistry to me was always really interesting. It's kind of the intersection between physics and chemistry. But quantum computers would be great to simulate chemistry because at a fundamental level, chemistry is governed by quantum mechanics, right? Chemistry is how does this atom interact with this atom in a way to make a molecule? And you can't do that without talking about the electrons. And the electrons are fundamentally quantum particles, right? They behave by quantum mechanics. They're not a ball that you throw off a hill and calculate the velocity. They're a quantum particle. And so you need to describe them with quantum mechanics. And quantum computers can directly simulate that. And I find it really interesting that there may come a point where quantum computers can simulate all of the things that we do in the lab right now in terms of chemistry research, right? So there might be a kind of a pipeline that looks like you have some company and they want to make a drug, right? They want to make a drug to interact with some receptor or some hormone, right? So what do? They figure out what is the structure of this hormone or receptor, and then they send it to a company that does quantum stuff. And that company will look at this molecule and they'll design 50 billion molecules, I don't know, some crazy amount of molecules to test, right? And then what they'll do is they'll run all of these through a quantum simulation and pick the 500 best, and then send those 500 best back to that company for actual lab testing, right? Right now, we have ways to direct research in terms of the chemistry that we understand, but just because of human limitations, we cannot simulate every single possible molecule before we, you know, do something with it. We have to test things in the lab. A quantum computer could really, really optimize that process and kind of get the pharmaceutical industry to move a lot faster with the drugs that they're able to make. So that's a really interesting kind of application.
Yeah. So David Deutsch was saying that he's a pretty big supporter of like this multiple worlds theory.
Yeah,
where
many worlds interpretation.
Many worlds interpretation, yeah.
Yeah.
So what are your thoughts on that? Because like that argument is really cool where, you know, we're simulating something that has more computation power than every single atom in our universe. So he's saying that there must be some kind of matter, parallel matter somewhere else that's contributing to this computation.
So
and yeah, what are your thoughts on that?
So the many worlds interpretation is really, really interesting. The problem with the many worlds interpretation is just that, as we know, there's no way to prove it, right? And so I think it's fine as a physical theory. David Deutsch, who is much smarter than me, believes it, right? And so it's got to have some merit, right? I don't necessarily believe it, but I don't also not believe it. It's one of those things where there are a bunch of different ways to interpret quantum mechanics. And to me, that's really interesting because it means that there might be more stuff that we haven't fully understood yet that might make it so that one of these interpretations actually does work out, right? And so I think it's really interesting, and I really don't sway one way or the other on interpretations of quantum mechanics. I focus more on the engineering and what it can do for me. Because even if we don't know how quantum mechanics works, right, in terms of whether it's the Copenhagen interpretation or the many worlds interpretation, what we do know is how to use it to make predictions and how to use it in the lab. Mm-hmm. And so I really like the fact that we can use it to make these machines that can do really cool stuff. The one thing that I will say, just to clarify with many worlds, is it's not necessarily saying that there are a bunch of different universes in the sense that you would think, right? So like often people think about universes as like in like a sci-fi kind of way, where it's like all of these little like bubbles in some higher dimensional thing that you can travel between or something like that, right? Yeah. Or like spatially located in different spots from another, but they're so far away from each other that you can't reach them unless you travel through some warp or something like this, right? Yeah. But I think, and my interpretation might not be fully correct. Again, this is super kind of deep into the weeds of interpreting quantum mechanics. But what many worlds says is basically, if you have some superposition in quantum mechanics, right? The probability, or the way when you measure that that superposition to be something, both measurements happen and you kind of get a branch point, right? But it's not like you've created new, because my first question with many worlds is, all right, you've created another universe by making this, this measurement. Where did all that energy come from? Where did all that matter come from? Why did we break conservation of energy, like all of these physical laws? And the answer is you didn't, right? Right. What happened is not that you created another universe, but they kind of branch off from one another, but it's still actually all of the same amount of physical stuff, which is really hard to wrap your head around. And I'd suggest to any of your viewers that are interested to kind of dive down the rabbit hole and figure out for themselves what they believe. Yeah. Because it's one of those things where it's one of those rabbit holes that you can just keep going down. It's really interesting. Yeah, I've been going through that rabbit hole. Yeah. We've all every physicist has been through the rabbit hole at some point. Yeah. Yeah. Pretty much, guys, that's about it for this video. Lucas actually has a YouTube channel as well. You guys should check it out. It's called Lucas's Lab. So I talk mostly about quantum computing, physics, and all things research and device physicsy. So yeah. Sweet. And guys, I've talked a lot with Lucas off camera, and this dude actually knows everything about quantum computing. So definitely go check it out. He's also just a super cool guy. So yeah, that's it for this video. Peace out. Got a feelings, head on the image, come and zip in it, no loss in image, just like the villain.